In this video, I'll introduce the idea of calorimetry and use it to show how you can find the final temperature of two items that are combined together. So in this example, I have 2 kilograms of 90 degrees Celsius water added to 4 kilograms of 30 degrees Celsius water in an insulating cup. So I've drawn it here. So there's a smaller amount of 90 degrees Celsius water in a larger amount of 30 degrees Celsius. What's the final temperature of the water? Well, if I put these two in contact with each other, I know that heat will travel from the higher temperature to the lower temperature. So there will be some amount of heat that goes from the 90 degrees Celsius water to the 30 degrees Celsius. There will be mixing of the water. You could physically mix it yourself, or it could move by convection to be able to mix these temperatures. It doesn't actually matter how the heat was transferred. All we need to know is that there was heat that transferred from one to the other. And heat's a form of energy. It's a conservation of energy problem. So the change in energy is zero. We don't have to worry about gravitational potential energy, spring potential energy, kinetic energy, nothing like that. The only form of energy we're dealing with here is heat. So the change in energy is also the change in heat. So the total change in heat has to be zero. That's the change in the heat of the hot water plus change in heat of the cold water. So zero is the sum of those two. That must mean that the change in the heat of the hot water is minus change in heat of the cold water. And Q is mc delta T, right? So change in heat of the hot water, the change in this is mc delta T hot. So m hot, C of water, delta T hot has to equal minus m cold, C of water, delta T cold. You see that C water is on both sides? So the specific heat of water is in both sides. It can cancel out. Now if one of these materials wasn't water, if it was oil, if it was a piece of metal, something like that, then these wouldn't cancel. You have to keep them in there. All right. So we've got delta T hot, delta T cold. Delta T for hot would be T final minus T of the hot initial. And delta T cold is T final minus T of the cold initial. We're given the initial of the hot and cold. That's the 90 and the 30 here. I've used two different notations. So 2's versus H's and C's. I guess I can change those. It's not too late, right? Still initial. So this is hot and this is cold. So the hot and that's cold. All right. So now if I put these into here, I can see m hot times delta T hot. So that's T final minus T hot initial equals minus m cold times delta T cold, T final minus T cold initial. So m hot T final minus m hot T hot initial equals minus m cold T final plus m cold T cold initial. Then we can rearrange this to put the T finals on the same side. So that would be T final times M hot plus M cold. Moving this over equals M cold, T cold initial, that's this piece, and then moving this over, plus M hot, T hot initial. So T final is M cold, T cold initial plus M hot, T hot initial over M hot plus M cold. And I don't have enough space to solve the rest of it, so we'll leave that as an exercise for you.